game and I have so much to do.
Okay, let's get going. First, we want to talk about homework. Okay. So, question one, again, we're dealing with this study of policing practices in North Carolina. Read in the data. And so the first part of this problem is to figure out how the data need to be formatted in order to pass it to the data block of the STAN program. And that is a little bit different than how the data needed to be formatted in assignment 2. We were just drawing from the prior predictive distribution of these things. A lot of people tried to just do exactly what was done on assignment 2 and found that the data didn't match up with what the data were declared to be in the data block of that STAN program. However, you can almost get the data into the format that you need just by like one line of dplyr, or you could do this with by, or you could do it with a sequence of loops. Doesn't really matter how you get there, but you need a data set that is aggregated to the police department / race level and has the number of number of stops, the number of searches, and the number of searches that hit for each of these. So we create that table, and then to be compatible with what was done in the paper, where the first police department is the largest one, and it is restricted to have its fee parameter and its lambda parameter equal to 0. I sorted it in order of in decreasing order of total number of stops. Obviously, Charlotte, Raleigh, Greensboro, those are the places that have the most stops of everyone, but you certainly see differences between number of stops of whites versus non-whites, etc. So once we get the data into this format, it is almost ready to go. We need to make a list, a named list of in R that corresponds to how the things are named and also what types they're declared in the data block of our STAN program. So we need a few additional things. Let's say N for the number of rows, R is 4, D is 100 for the number of races in departments respectively. And then the other thing, which a lot of people were tripped up by, is you need to pass an integer array for R and D, indicating what race, what department we are talking about. The STAN language only involves integers and real numbers, and so you can't just pass like a string to STAN, nor can you pass a factor to STAN, but you can coerce things to a factor in R and then coerce them to their integer codes. And so 1 is Asian, 2 is black, 3 is Hispanic, 4 is white, etc. Do the same thing with the police departments, and then give it N the number of stops, S the number of searches, and H the number of hits, and we're ready to go. Questions about that? Okay. So the first thing we can do, you didn't actually have to do it, but I did it, is called the original model in STAN, or actually the one that's called model.stan on Canvas now has a few cosmetic changes in order to get it into sort of the style of coding that is preferred these days. But I didn't change the thing about the largest department, Charlotte and Mecklenburg, being restricted to 0 on the fee or the lambda parameters. Now, if you run that just with the default settings, one, you may have some difficulty getting it to initialize, particularly with models like this that have a lot of parameters. Sometimes STAN can't even get going, and that is due to the fact that by default it is drawing the initial values uniformly between -2 and 2 in the unconstrained space. Remember, we talked about the reason why, or part of the reason why you have to declare things in the parameters block is having lower bounds and upper bounds and types and stuff is necessary so that Stan can do the transformation from this unconstrained space where from its perspective, the sampling is happening because that corresponds to what you need to do Hamiltonian Monte Carlo. And then it transforms it using one-to-one transformations into the parameters that you declare in the parameters block, takes care of that Jacobian change of variables for you. And then from then on, it looks to you as if it's doing the posterior distribution of the things that you declare in the parameters block. In any event, the initial values by default are taken between uniform between -2 and 2 in the unconstrained space. And this was also a little bit of an unfortunate choice that we made in 2011 that probably wasn't that good. Should be using a narrower interval than -2 to 2, because for a lot of models that have a lot of parameters, if you get something in the unconstrained space that's too close to 2, you'll get a realization of the parameters that results in like the log kernel going to -infinity or something like that, and then Stan can't even get going. So when you have that, one possibility is to pass initial values explicitly, and that's documented in the Stan function, but usually you don't need to do that. Usually you just need to specify the init_r to be some value that's positive but less than 2. Init_r is the radius used to draw the initial values uniformly in the unconstrained space. So instead of drawing from between -2 and 2, you draw between -0.5 and 0.5. And that allows this model to at least get going. However, it certainly takes a lot of time, and at the end you get a warning back saying there were tons of transitions that exceeded the maximum tree depth, which by default is 10. And that is to say it was taking at least, for 1465 transitions, at least 10 leapfrog steps without hitting the point where it would make a U-turn and start to double back on itself and get stopped because of that. So in other words, it was sort of still going to the U-turn point when it hit its upper bound of 10 leapfrog steps on those transitions. And so there's a fairly straightforward fix to that problem, but it involves rerunning it again with a higher value of max tree depth, which I did not do in this particular situation. If you look at the R code in the GitHub repository, the authors of the paper did a maximum tree depth of 12, and that was apparently enough to get these warnings about the transitions to go away. But in this case, I wanted to show, how you can sort of diagnose things that are going wrong. And so as I suggested, to look at the pairs plot, a number of people have gotten error messages or crashed their RStudio trying to call the pairs plot on all of the parameters, which in this case was like, 1,000 or something like that. That is going to make a density plot for every two-dimensional pair of variables. And even if it didn't crash your RStudio session, it would be completely illegible for like a double-digit number of margins that get, that choose 2 paired together. So these things are really only reasonable if you specify a handful of parameters that you think to look at. In this case, I am contrasting mu of phi at the department level with phi for the 4 races, and looking at the log posterior kernel, which is LP__. When you do this, you see that there is pretty severe positive correlation between the race parameters on phi at the sort of state level before you get into the hierarchy stuff. So this is at the top level of the model. There's a little bit less of it's still positive correlation. It's still pretty strong, but there's less of it going on for the first race compared to the other. This is for Asian, and there's so few of them in North Carolina that the correlation is a little bit more diluted. But certainly for whites is 4, blacks is 2, Hispanic is 3, you have a very strong positive correlation on these phi parameters. Conversely, if you compare any of these to mu of phi at the department level, so sort of the state level expectation of these phi parameters by department, we see a strong negative correlation between this and any of the phi parameters for R. These yellow dots indicate transitions where it exceeded its maximum tree depth. And so we see a pattern here. Right near the mode, it's mostly not yellow, it's blue. So if it starts out at the mode, it's usually going to be okay. But if it starts out a little bit away from the mode, particularly if it has to go out into the tails for that transition, then it'll often take more steps than the default allots to it, which is 10. There were no divergent transitions, but if there are, those points would be overplotted in red by default. So that's a little bit how to use the pairs plot. And so we have these severe positive correlations, but it's important to emphasize that doesn't mean that there's anything wrong with your posterior distribution. In light of these data, it's entirely reasonable for you to have very positively correlated beliefs about the phi parameters across the 4 races. But what it does mean is that this is a very difficult posterior distribution for Stan, or by extension any other MCMC algorithm, to sample from, because basically, you know, if this is like the pair between Hispanics and whites, it has to walk a tightrope to get from one tail to the other, and this goes from like -6.5 to 5. So you know, it's a reasonable distance there, but it has to sort of walk along this ridge, and if it, you know, goes this way or goes that way, the posterior kernel rapidly goes to like -infinity. So there's no density there, and it's got to do this not just for like this pair, but you know, for all the pairs that have a severe correlation. And in order for it to do that, it has to take very small steps. It's like walking on one of those like narrow path things in the mountains that if you like step one way or another, you fall off the mountain. Stan can do it, but like, you know, someone who's walking on those things in the mountains, you have to take very small steps, and you have to go in, you know, relative terms a long way. And so it takes 10 or more, in some cases, leapfrog steps, you know, from you to get across, you know, from one side of the posterior distribution and the other, in order to have, you know, a good chance of being able to draw a footprint from where you've been that is, you know, a random draw from this posterior distribution. And so, you know, in principle, Stan can handle, or you can define in the Stan language, any posterior distribution as long as the log kernel of that posterior distribution is differentiable with respect to the parameters. In practice, you may have to take very small steps in order to do that faithfully. And in practice, the step size that's small enough for you to do that may be smaller than the smallest non-zero number that can be represented on a computer. Or moreover, if the step size has to be like this small, then the numerical error in calculating the the posterior kernel and the gradient and the leapfrogging step of all that, you're going to get like more numerical error than you have width on your path walking across the mountain. And in that case, you're going to fall off the mountain, get a divergent transition, and die. So, and best case scenario, you can barely take small enough steps. The steps are small enough, you don't get too much numerical error, and it just takes a really long time. But that's the best case scenario. So just because you can define something in the Stan language doesn't mean it's feasible or practical or rapid to get draws from that posterior distribution, but at least Stan is going to be able to tell you warning messages when you find yourself in that situation. Unfortunately, the warning messages don't come out until the end, so you may have to wait a long time before seeing that, but you can start with a smaller number of iterations, which I think a number of you did.
So, like, if it says, oh, initial, like, number of data example, that's the message that I got in the very beginning. So, is that, I mean, should I see that sort of as like a picture for, like, not running Stan and waiting?
No, that one basically just means the Stan developers chose a bad default value of 2 there. And you can usually get around that particular problem just by making that radius of initial values smaller. However, even if you do that, you may or may not be that successful drawing from the posterior distribution, but it ought to at least start. Becca.
Is there any reason, do you lose anything by making the init r smaller, or can that just be like a standard thing you should always make it run?
Well, it doesn't really make it run faster, but it enables it to get going. Some of the convergence diagnostics rely on the fact that the draws are like over dispersed. So you start in like the 4 corners of the parameter space and they all come together. If you like start all the chains like basically just the epsilon away from each other, then it might appear as if they've converged, but they really just haven't explored the whole parameter space. So you kind of want to make it as big as you can, but still small enough to where Stan can get going. And once it gets through its first iteration, then it will usually complete at the end, but that may take a while. Rishika.
If you're designing a one set, you also like these nanometrics, like is it just advisable to change or to like keep on working with the configuration until you get something? Like how does it impact the results?
Okay, so they just kind of increased the max tree depth and increased the number of iterations and dealt with it. But perhaps a better way to combat the problem in this particular case would be to do a reparameterization of the phi r's in terms of another level of hierarchy, a mean, some zr, which has a standard normal prior, and a sigma. So originally the prior is like 0.2 or something like that on the phis. But if you do this reparameterization where phi r gets declared in the transform parameters block, zr is defined in the parameters block, gets a standard normal prior in the model block, then having this common mu here breaks up a lot of the, well, really, since phi r is now a transform parameter, it doesn't really matter how highly correlated in. What Stan is interested in is the z's. But those are going to be mostly uncorrelated with each other, or at least less correlated with each other, because you've basically allowed the mu's to account for this like common phenomenon in the data that, if we think, there's a high phi for blacks, then we also think there's a high phi for Hispanics or something like that. So that kind of, you're still going to get high correlation between this mu and that mu for the departments. But you at least break up the correlation among these by doing a reparameterization that makes the phi r's transform parameters, and you have this sort of z thing with the standard normal prior that's declared in the parameters block as your primitive. Now, when we go to relax the assumption that the phi for the largest department and lambda for the largest department are 0, it gets even worse. I only did 500 iterations here, but all of them had a transition that exceeded the maximum tree depth. You can see the correlations are now even more pronounced, more extreme, more universal. And that's fundamentally due to the fact that in their model, you have this phi by race and district crossed. That is the logistic CDF of the difference. That should actually be a plus there. between phi for the department and phi for the race. And so you can add or subtract any number to phi d and do the opposite thing to phi r, and you would get the same phi rd, and consequently all the observable implications of this data generating process would be the same. Now, the original paper that imposes this restriction that phi for the Charlotte Police Department is 1, you know, we're saying, okay, we're using all these weakly informative priors. We're not assuming from the outset that the North Carolina police are discriminatory, but they have this one thing that is like very informative, because this is basically the same as, you know, having a normal prior with a mean of 0 and a standard deviation of 0, whereas like all the other ones have a standard deviation of 2 or whatever it is they give it. So that is like a very strong piece of prior information. I'm not sure it really, or their ultimate conclusions are going to be that sensitive to it. But if for some hypothetical reason, the largest police department, that being Charlotte, had like a lower search threshold for whites than it did for non-whites, then all the other police departments in North Carolina would look more discriminatory against minorities, even if they were being race blind. It's just in comparison to the largest department is really what their results are saying, rather than in absolute terms. So I think it would have been better if they had relaxed that assumption, maybe done some other reparameterizations, but it would be a hard model to get the posterior distribution drawn from. You'd likely have to increase the max tree depth up to, 15 or so in order to get rid of, all those, messages, and it would just take a long time. Sebastian.
So it seems like with this reparameterization, doing these just a little bit above, you're having sort of like what's computationally efficient inform your model, and not just how you live the world.
Right.
So yeah,
that is true. But I didn't, in so doing, I did not change my prior beliefs about phi r. So at the beginning, I assumed they were normal with mean whatever and standard deviation 2, I guess. By putting a standard normal prior on ZR, multiplying it by sigma, shifting it over by mu, I still have those same normal prior beliefs about phi r. I've just made it a transform parameter and use the scale location property of the normal distribution in order to enforce that. So I didn't change my beliefs, but I did have to make, more entries in my STAN program in order to reduce the posterior correlation in the parameters that STAN thinks it's sampling from, which is like Z and sigma and mu and everything else. The stuff in transform parameters is really just a human concept. They're intermediate parameters that go into the likelihood. But, from Stan's perspective, they're not primitive. And so that doesn't affect the sampling efficiency or lack thereof in this model. So you're right. We're doing stuff for purely computational reasons, although we have a good justification for that, which is if we didn't do that, it would be very hard or impossible to faithfully sample from this posterior distribution. But we're doing so, at least in this case, and in a lot of cases, using transformations, which is one of the reasons why we're emphasizing this at the beginning of the semester, that don't change our beliefs. They're just like Jacobian here, Jacobian there, in order to get a posterior kernel where the second derivatives are less extreme. They're closer to 0. But the margins of the posterior distribution that we care about are not being changed by these transformations. So if you had normal prior beliefs about phi, you can do this transformation and have the same beliefs about phi, but phi is no longer a parameter, it's a transform parameter. So you will see in a lot of cases, the things that are of substantive interest to a human are going to be in the transform parameters block, maybe in the generated quantities block. And the stuff in the parameters block, less interest from a human social scientific perspective, but there's transformations going on from the less interesting things to the more interesting things that preserve your prior beliefs about the more interesting things. Yeah, and you see that a lot with the QR thing. Beta is of interest to the human, theta is not. Theta being the coefficients on the Q matrix in the QR decomposition. But we can, do the sampling in theta space and then untransform at the end to get coefficients in X space, the posterior distribution of beta. So all of these things where you see people doing transformations and you're like, well, why are they doing all that? Why are they jumping through those hoops? It's to get a good effective sample size in a reasonable amount of time. And hopefully, if you do it right, without sort of, changing what you believed about the things of interest as you do it. Yeah, especially.
And then if you sort of conditional on like your model converging, they expect that doing things like changing depth of the number of iterations, as long as it's reasonable, you're going to get pretty similar results.
But you want to, as long as you have enough effective sample size, then yeah, probably. But you need to look at that as well. And you need to make sure the things that you're calculating the effective sample size of, there's actually, a finite mean and a finite variance and stuff like that to, make the Markov central limit theorem hold and all sorts of things like that. But basically the bottom line is the effective sample size. Are you getting enough effective draws for your inferences about whatever you're interested in to be reliable? And it's not the case if you were to do like, 4 more chains, you would get a different answer just due to variability in the chains. All right. So, okay. That's it for question 1. Question 2 would perhaps be easiest, although it's not the route that a lot of people took. To use BRMS to make some stand code that resembles the stand code that you need for the second problem. So if you just start off with like a plain probit model for is the person in the labor force, then you can tack on the other part of the model after that. So when you call make stand code, BRMS generates this for a probit model, and it has comments telling you what all is going on. As you can see from the stand syntax, I used some predictors that were plausibly exogenous. How many kids do you have at the age of 5? How many kids do you have between the ages 6 and 18? What is the age? What is the level of education? And then intercept that varies from one city to the next with a normal prior around it. I put, since this is a probit model, normal 0-2 coefficients on the, or normal 0-2 priors on the coefficients, which if anything was already too weak. So we get all this, and then we can make the appropriate modifications for a selection model, more advanced than a probit model, with 2 binary endogenous knowns, such as like, are you in the labor force? And if so, do you have a managerial or executive job? Or do you decide to vote? And if so, who do you decide to vote for? Things like that. So in this case, it might look something like this. We paste in the function that I gave you. We'll get to calling that later on in the model block. Data block is pretty much the same. I changed y to ys to indicate this is the selection variable, and I added another integer array y of size n. I define this as having that should have a lower bound of 0 and upper bound of 1, but I define this as having a lower bound of -1, upper bound of 1. So valid values for integers are -1, 0, and 1. And I'm saying I'm just going to code this as -1 if ys is 0. And so if the person is not in the labor force, we don't observe whether they would have had a managerial job if they had been in the labor force. And so only the 0s and the 1s in yo for the observed thing are relevant. This part was the same as what was generated for by BRMS. It has mostly to do with the city-to-city intercept deviations. And then this is all the same. In the parameters block, I put a comment saying, well, these pertain to the selection part, but I didn't actually change them from what BRMS did when I just generated a probit model. And then I added some parameters using twos and Greek letters and etc. for the parameters that go into the outcomes part, conditional on you being in the labor force. Also a correlation row that's restricted to be between -1 and 1 that captures the correlation between the errors in the utility for the two parts to the model. And so sort of the essence of the Hegman approach, which he developed like back in the 1970s, at somewhat different time, was in trying to explain like why it is that women work less hours or paid less and things like that. One explanation for that phenomenon could be correlation between the error terms and the utility for the two parts in the model. And so the women, like in Hegman's time, well, he's not dead yet, but when he was younger, the women that we observed in the 1970s being part of the workforce had this selection process where there was some reason to believe that those were the really good workers and the less productive workers were less likely to be in the labor force in the first place. Transform parameters. This is the same. I created another one here for the outcomes part of the model that could also have an intercept that varies from one city to the next. Model block created the linear predictor for the selection by multiplying the matrix of centered predictors by its coefficients, adding on the temporary intercept that corresponds to centered predictors, and then adding on the deviation by city in the intercept using J1 to index these city-to-city deviations. Have a bunch of priors for the selection part of the model, and then we get to the likelihood. Now this is all enclosed in an if statement saying not prior only. If you go back to this thing in the data block, there's an int that should be constrained between 0 and 1, but something that you can pass through BRMS, you can say this is true, in which case it'll get coarse to 1. In which case, just draw from the prior distribution only. Don't condition on the Y data. And so you stand, things that you're drawing from a posterior distribution, but you're not conditioning on any data. So you're really just using stand to draw from your prior distribution. And then you can use those draws from the prior distribution to understand the implications of your prior, or to draw from the prior predictive distribution and understand what your model and your prior beliefs about the parameters implies for the distribution of the data that you expect to see. But in the usual case, prior only would be 0, and so not prior only would be true, and so we're going to condition on the data, and we need likelihood statements. Now these, the stuff in this block follows from page 2 of the vignette of the sample selection package, which implements models like this from using frequentist estimators. And models like this, when using frequentist estimators, tend to go extremely badly. You need very, very large sample sizes in order for the asymptotic normal distribution of the estimator to hold across samples, which may not be that much of interest anyway. But the idea of a sample selection model, I think, is very important for the social sciences, where we have a lot of this stuff going on, and estimating it to get the posterior distribution, not particularly difficult, although the parameters may have large tails in the posterior distribution. So if someone is not in the labor force in the first place, then we basically just have a probit model, add on the logarithm of 1 minus phi evaluated at A to S, and that's pretty straightforward. If the person is in the labor force, then there's a 2-part contribution to the likelihood, which is why we need the binormal CDF function that I supplied for you, and we pasted in the functions block. So basically, if you are in the labor force, but you don't have a managerial job, then this is the contribution to the likelihood. And otherwise, if you do have a managerial job, then this is the two-part contribution to the likelihood. Here, I've simplified one thing. There was like, you put in alpha something minus the linear predictor, but if you were 1, then that would be referring to alpha 3, which was said to be infinity. And if you have infinity minus something that's still infinity, and the probability that a random variable is less than positive infinity, it's just going to be 1. So the bivariate normal CDF really collapses to a univariate normal CDF on the other margin, in this case, A to S. But there's still a bivariate normal contribution coming from the other part of the model. So that's really just translating what's on the second page of the vignette into stand code. And then there's priors on the outcome part of the model, which were very similar to our priors on the selection part of the model. I did this just to illustrate that because addition of terms to the target distribution in logarithms is commutative, it doesn't matter what order you do things, or it doesn't matter what order your target plus equal statements occur in your model block. The only thing that matters in terms of order is a variable has to be declared and defined before you can use it. If you use something while something still has NAs in it, then you're going to get error messages and stuff like that. I didn't explicitly put a prior on row. Certainly could have, but by not doing so and by declaring it to be bounded between -1 and 1, then the absence of a prior is basically just saying have uniform prior beliefs on that interval about rho, which is probably not what an economist would believe. Economists more likely to believe that rho is positive than negative, indicating this sort of positive selection where good workers are more likely to be in the labor force, not as good workers, less likely to be in the labor force. Did you have a question, Rashika?
I just have a question about that.
Yes.
Is it the same thing as a normal
Phi is normal CDF, no log. So I had to do the log here. But normal underscore LCCDF, that's the complementary CDF logarithm. So the logarithm of 1 minus the CDF, the probability that you're higher than this.
So when we define is it normal to the error term in there, or is it?
That would be non-normal, or it would also be atypical. Yes.
Like to add an error term, because this is like x times beta plus.
Right. So any error term that you put into eta would be observationally indistinguishable from the error in utility. So you wouldn't be able to separately estimate its variance. So there's no need to do so in this case. But most of the time, when people do this, like we did a little bit of exception of this when we did like interaction terms between age and income, and we weren't sure that it was entirely a deterministic relationship. But usually when constructing linear predictors, we're doing so in a way that they're deterministic, conditionally deterministic. So if you know the coefficients and the intercept and all this, then eta is no. And so the only unknown part about eta is because we don't know the coefficients and the intercept. And so marginally it has a distribution. It's a random variable. Conditionally, it collapses to a spike. Then in generated quantities, I added a little bit of stuff to draw from the predictive distribution. Paul also has this, and we have it in our stand arm, where you center the columns of the X matrix in order to get the intercept that is more independent from the coefficients. And then in generated quantities, you shift the intercepts back by multiplying by the vector product of the vector of means and the vector of coefficients. And so the intercept that you see on the outside corresponds to the parameterization where the x's have non-zero means. But anyway, you can use either one. And then I declared an integer array for selection, integer array from outcome, where I can draw from the predictive distribution. And so if I do prior only, these are draws from the prior predictive distribution. If I actually condition on the data, then these are draws from the posterior predictive distribution. But the mechanics of it are the same either way, and this just corresponds to the generative process that was outlined on page 1 of the vignette. So we construct these EDAs, which are the linear predictors of utility, the same way we did in the model block. We draw an error in utility for selection from a normal distribution with a standard deviation of 1. We add it on to the linear predictor to get our utility for selection. And then the error for the outcome is conditionally normal. So these two things together form a bivariate normal distribution, but in the form of a marginal distribution composed with a conditional distribution. And the conditional mean of the error in the outcome part is rho times the residual. And since the expectation of 0, that's just means multiplying by the error that you just got through drawing. And then the conditional variance, or the conditional standard deviation, is not 1, but rather the square root of 1 minus rho squared. So it's only equal to 1 when rho is 0, which is to say there's no dependence between these two things in the first place, and it's like doing two completely separate probits. But that's a special case, and one that is sort of unlikely theoretically, or at least it kind of was in the 1970s. Anyway, that's the error that goes into the utility for the outcome. And then we can construct these binary variables just by evaluating the Boolean condition, are they greater than 0? And so when you do this for the predictive distribution, you're going to get 0s and 1s on both of these. And so you may be drawing the case for someone who chooses not to be in the labor force, but if they were in the labor force, they would have a managerial job. But we don't observe that in the actual data because of the selection mechanism. People who are not in the labor force don't have jobs at all. But that's important to estimate the rho, to estimate everything else. So we can make a list of data to pass to Stan by calling make Stan data. We don't have any YOs yet, and so we need to say we want to draw from the prior distribution to get prior prediction. So we just make a placeholder for YO where everything is -1, rename Y to YS and null that out. We can draw from Stan using like just one chain and just one draw after warm up to get one prior predictive distribution. We can then look at our predictions with something like this. And what we find, at least for this seed, and when we only do this once, everyone was drawn to be not in the labor force. And so that would really imply that the priors that we had on the selection part of the model were way too weak, even though they, normal 0-2 doesn't seem that weak. But if you get a draw of those that's like everything negative, then you can end up with something like this, where in the predictive distribution, it predicts no one is in the labor force, which is a ridiculous thing, even in the 1970s. But we can feed that back to make sure our model is working, and we actually find that we get warning messages. If you try to do this model and you have no one in the labor force, then there's no information with which to estimate the outcome parameters, and you can easily get warnings like this where Stan is saying, like, I'm having a hard time doing this because I have no data. Question? So that did not go well, and it sort of suggests that our priors should have been tighter. But the thing that I mentioned in lecture last week, a more systematic way of doing this involves repeating that process multiple times, looking at the whole distribution, because if your thing is working well and you're conditioning on data that was drawn from the prior predictive distribution, the posterior distributions that you get out theoretically cannot be systematically different from the priors that you put in. And so you can verify that your estimation thing is going to work before you even do it. Questions about question 2? Sully.
How do we know, like, from the very first line that like COVID is the appropriate in next half?
Well, the model in the vignette is basically a bivariate probit with only partial observability. And so the closest thing that you can generate with BRMS would be univariate probit. So it's basically a univariate probit for are you in the labor force, and then a conditional probit for what happens to you once you're in the labor force. And so you got more than halfway there by just asking BRMS to generate you code for a probit model. But yeah, it's because of the bivariate normal. And so probit is the univariate analog of that. Andres?
So how would you like fix here the transitions? How would you go back and fix?
Yeah, well, I should have used priors that were on the coefficients that were tighter than 0, 2. Or I should have used prior on the intercept that was tighter than whatever the default is. I think it's like 0, 10 or something kind of ridiculous like that. So I should have used priors that are more concentrated around 0. So I would get predictions where some people, women, are in the labor force and some are not. That's sort of minimum requirement to have reasonable prior beliefs, because we know that to be the case among any like random 783 women that you have in your data set. Okay, other questions about question 2? Sebastian?
So would you like frame that decision around the prior being like what, rather than like, no, I'm actually changing what my prior beliefs are, instead it's the numbers I set up for the prior didn't actually translate to the
right. Yeah. So implicitly, you believe that if you get like a non-trivial number of observed women, some will be in the labor force, some will not. Like any reasonable person would believe that. But the priors that you chose put, a positive probability on like none of the women working. And so that contradicted your actual beliefs. And really, you just kind of made a mistake in expressing your beliefs about what the coefficients were, but you needed to see it before you realized what your mistake was. Depends on how correlated the x's are, stuff like that. Okay, question 3. Christina? Uh-huh.
I'm not sure what the last part is that we're adding.
The last part is for the city, the deviation and the intercept from one city to the next. So those are declared, yeah. So the Z are the unscaled group level deviations, and then in transfer parameters, you bump them up by the unknown standard deviation to get the scale deviations and the intercept from one city to the next. So that was the Stan analog of this piece in my R formula. So that's what that is. Okay, question 3. What did y'all think about that? Question 3.
I think it seems there's how the arguments about not specifying all of these. Seems to kind of mirror in some ways to me the Rails bias and kind of process. That's kind of where I was going. Whether it's acceleration could be.
Yeah, I mean, so in that example where Humphreys and Jacobs really taking into account all the things that a qualitative person, if they had really studied, would have been taken. Yeah. Okay, good. What else, Sebastian?
Can you make this comment of like something? How can you prove that whatever caused the, I can't remember that term, this thing caused PR when it could have been something else that caused PR?
Mm-hmm.
And in public health, we don't use the idea of two exclusive causes, because that's not how It's very rarely that one, but it could certainly be the case that multiple things did cause it. If you knock out one thing, any other thing that doesn't mean that one didn't. So that seemed like a weird, like consisting that seemed inconsistent.
Yeah. So maybe adding a richer structure into predicting who is of what type that could depend on multiple variables rather than just the single X, and or maybe looking for multiple clues that would pertain to one or the other mechanisms that could be at play for any particular observation.
Yeah, but I guess inference is also like, it's, to me at least, it's satisfying to say, in the absence of factor X, why it didn't occur for these cases, why it wouldn't have occurred. And that doesn't mean that in the absence of, X2, why also wouldn't have occurred.
Right.
Or she's talking about, you're not testing the effect of other factors, but of course other factors would also cause it. So I guess what I'm saying is, yes, you could include a lot of other factors, and then in certain ways it would be more qualitative, you're having more hypotheses, but that doesn't make what they did invalid or testing this one.
Right. So, if you don't have clues, you have this sort of 2 crossed with 2 things that X and Y could be, and then, you go from 4 to 8 when you add the clues, and if you start, taking into account all these other things, you have 2 raised to the power of like all these other things, even if they're binary, of cases, or not cases, but cells that you have to consider. But in principle, you could work out a probability model that would tell you the probability of falling in each of the cells, and then update your beliefs about those things. Robert?
You complain a lot about the where do the priors come from on the p-values, sort of say when they pulled out of thin air, seem rather intellectually ungenerous, given that it was part of the talk. They came back and said, look, there is a lot behind this. Yes, there's an enormous amount of uncertainty. Also, you can quantify your uncertainty about those values. You can, part of the value of the framework is that you can say how uncertain those estimates are, and that can influence, how certain the results of the model are.
Yeah, that was the main thing that I sort of took from it. So she sort of said, where does the 0.9 and the 0.5 come from? And McCartan kind of, I think, got himself in trouble. And I've seen this a lot of times when people try to explain a Bayesian thing, but to like simplify it down. So as part of the presentation, they just said, okay, assume your beliefs about phi, or, this one is 0.5, the other one is 0.9, as if you're certain about those things, just to make it like simpler. So you don't have to update your beliefs on those to work through the logic of how the fees relate to the, probability of a treatment effect and stuff like that. But that's sort of equivalent to a beta prior with this or that expectation and 0 variance, which is not something that, political scientists would really make sense to them. We're probably going to be highly uncertain about these clue probabilities. But maybe it's putting words in our mouth, but I don't really think so. A sort of undercurrent of this is that there might never be a compelling justification for having a strong prior belief about some of these clue possibilities. Now, I don't think, and in the presentation they didn't talk about, well, you could have just a uniform prior over the 0-1 line on all these things, and that would sort of maybe reflect the close to being very uncertain about these things. But one of the points that McCartan makes, that if you do that, you're unlikely to learn much of anything about any of the other parameters from the cases where you spend all this time and money to go get clues. If you're, saying, okay, I have uniform beliefs about the probative values and stuff like that. And maybe even stronger translation of what she seemed to be saying was that, well, if you're using probability distributions to describe your prior beliefs about these, whether you have some justification for that or not, then the research is quantitative rather than qualitative, because you're using probability distributions and Bayes rule and Stan and all that. And I think that is probably something that wasn't that clear in the presentation, but I don't think that is a very strong point, at least in the paper. Humphreys and Jacobs make, the argument that it's really the logic of Bayesian updating and Bayesian inference conditional, for everything that you don't know, conditional on what you do know, regardless of the form that the known data takes, whether it was sort of cheap data that anyone can download or expensive data that you have to go learn a foreign language and live in some place for a considerable amount of time before you can get the access to interview the people to find stuff about the clues and whatnot. And I think that emphasizes that this approach to science of using Bayesian estimation is really just a mechanism for managing your beliefs in a self-consistent way, to be explicit about what your beliefs are going in, and using software and probability and math, but it's really more logic to ensure that your beliefs are being updated in this self-consistent way. And if you're, I think, thinking about the implications for what would be the most efficient research design in light of your prior beliefs about the parameters. That was another important part about the paper that unfortunately we didn't have enough of a time to really talk about. But depending on where your beliefs concentrate in the parameter space can tell you stuff about the expected efficiency of getting more intensive cases, or fewer of those and more of the other, or something like that. All righty, question, Mark Salif.
For these kind of priors on the parameters, like if you have different kinds of evidence that you use, is there like a specific rule how you like set the uncertainty, like the deviation of like for instance the distribution? Because if you have like, especially if you were trying to accumulate knowledge from like quantitative and qualitative types of quantitative, especially like, is there any way to say okay, like that's a deviation?
No. Okay. So more about missing data. Missing data. More about the disclosure thing, which if you haven't figured out by now, last day of the semester, you probably have serious listening comprehension problems. But for those of you who may be tuning on YouTube for first time, we're at Columbia, I'm at Columbia, Stan's at Columbia. You stand for stuff not at Columbia, and that creates the appearance of a conflict of interest that you should be aware of before using Stan to deal with missing data. So what we talked about last time was that it's relatively easy, at least conceptually, to just say, okay, missing data, I'm going to put that in the parameters block, and I'm going to update my beliefs about what the values are along with everything else, and I just need a few lines different in my Stan program. And that approach is sort of this approach where we're going to basically update our joint beliefs about everything all at once. And at least theoretically, that makes a lot of sense. In practice, it's harder than that. And in practice, at least before Stan, but even still today, it doesn't exactly go the way it sort of theoretically suggests that it would be easy. So we can write down the posterior PDF, taking into account that there's missing data that we don't know, theta parameters that govern the data generating process, phi parameters that govern whether the data is missing or observed, conditional on our observed data, and conditional on our two-dimensional array, which tells us which data point for which column was observed and which one was not. So we can factor that posterior PDF as the product of two posterior PDFs. One, the PDF for theta given the union of the missing values and the observed values, multiplied by conditional distribution of the missing values and the phis given the observed values in the R. If you just use the multiplication rule, you get this. Now, in order to actually do that, you would have to take this piece here and integrate the thetas out in order to leave yourself that piece there, and that may not be possible in practice, but you could do it in theory. And so this factorization of the posterior PDF suggested conceptually, well, what we have here, theta given the union of the missing and the observed data. So that's basically the posterior PDF that we would have if all the data were observed in the first place. That, you know, if I didn't distinguish between M and O, we just have, you know, posterior distribution of theta given data. And then, you know, we have this other part of the posterior PDF for the missing this process. So if we could integrate out theta and then somehow draw from this posterior distribution, then we could do like regular Bayesian inference for theta. And this led Don Rubin, again back in the 1970s, which is to say way before Bayesian inference was really possible via MCMC, much less Stan. And he proposed the above thing could be approximated using the following multi-step technique. Draw m times, where m is greater than 1, from the posterior distribution whose PDF is this, so the posterior distribution of the missingness, and then take those draws from the posterior distribution of the missingness, create m complete ed data sets by filling in the missing values with the posterior draws of the missing values, and then take those m completed data sets, estimate your model, which is to say a frequentist model, m times using each of the m completed data sets as if there was no missing data in the first place, and then average your m point estimates together. There's a slightly more complicated thing to get the standard errors, but it's basically do the analysis m times and average. And so pointed out in the 1970s that this would be a more reasonable thing to do than what everybody back then was doing and what everybody is still doing today, which is just like dropping all the observations that have any missingness on any of the variables that go into the model. And that is only a valid procedure if the data generating process is missing completely at random. And there's a few more exceptions, but basically it assumes missing completely at random, which was the strongest of the assumptions and the one that is least plausible in the social science. So, you know, that's a little bit of the theory of it, and that's where Rubin was coming from in the 1970s, where, you know, Bayesian approach, or at least the pure estimation of it, was, you know, completely impractical. Nowadays, people still basically follow what he said in the 1970s, even though we have more computational power, but they take a whole lot of shortcuts, even more shortcuts in the process. So researchers, if they're going to do multiple imputation, almost always assume with no stated justification and probably little unstated justification that the data generating process is actually missing at random. And that implies that this posterior PDF that conditions on R doesn't actually provide any information about the missing values after you've conditioned on M. So R drops out of this conditioning thing, and you don't have to worry about a model or a part of your model for R. Now, a lot of people make this assumption, or the software makes their assumption for you, because they're like, well, I don't want to construct a model for R, as if the data generating process gives a shit about what you want. Like, R may very well provide information about what the missing values are. That's the essence of selection. And that's something that you really have to take into consideration. It's what makes social science research somewhat unique. And again, you have to consider this in a historical context, that back when Fisher and those people, even before there was social science, they were studying agriculture and stuff like that. So I don't think they had as severe missingness problems, but they certainly didn't have selection problems of the sort of thing that we have today when we're studying humans in the social sciences. And so, you know, he derived this whole frequentist thing where the answer to the question, why do you observe these values and not values from, you know, some other observations, was straightforward. There was an explicit randomized sampling mechanism where some observations were randomly taken from the population and others not. Now, that was, you know, always a bit of a fiction, but especially today where we don't even really pretend in a lot of situations that the data that we have are a random sample from some well-defined population with a well-defined random sampling mechanism in a lot of cases, you have to ask yourself, why do I see these data and not other data? It's not a simple, like, there was a randomization thing going on, because the people chose whether to make that data available to you. And so you have to think about that process, and that you have to, your thinking about that process has to inform how you would make a model for R. Anyway, another shortcut, instead of explicitly integrating theta out of the original posterior distribution, which you can't do analytically anyway, we'll just approximate this posterior distribution with like a multivariate normal, which we'll talk about briefly, or a Gibbs-ish, not quite Gibbs thing, where you loop through the variables and model each one conditional on the others. And moreover, when people do this in practice, instead of obtaining genuine posterior draws of the missing values, they're just going to use some deterministic estimator, draw from the sampling distribution of the parameters, and then use those realizations to draw from the predictive distribution. But it's a very Bayesian idea, and it's an idea that originated by a very Bayesian person. It's only the shortcuts and approximations and the fact that at the end you get to sort of approximate this with the mode of a likelihood by doing some frequentist estimator m times that makes people who are, you know, only going to use frequentist estimation methods anyway comfortable with using multiple imputation. But really all you're doing, and we'll see this maybe hopefully clearly, is getting the posterior distribution of a point estimator averaged over the true values of the observations that went missing. And so this point estimator is really like a generated quantity, and you're getting the posterior distribution of a point estimator averaging over the missing data. So it really is Bayesian, but you can see how people think it would be frequentist. So one of the most popular things for doing multivariate normal imputation is R package, and other software as well has it, that does so-called multivariate normal imputation, again using frequentist stuff. But it is pretty simple to make a stand version that does the vast majority of what Amelia does, but does it in a genuinely Bayesian way and is open to, you know, further extensions and improvements of this model. So we declare in the data block the number of observations, the number of observed values, the number of variables that we're putting into this multivariate normal thing, our R array, which is constrained between 0 and 1, and 2-dimensional, and a long vector of the non-missing values. So these are our XO, and those are only going to correspond to the values in the original data matrix where R is 1. So we have a long vector of observed things coming out in row major order. Then in parameters, we declare a complementary vector xm for the missing values that we don't know, and the mean vector and the Cholesky factor of the multivariate normal distribution that generated both the observed values and the missing values. So that's the data block. In the model block, we start by declaring a local vector, row vector of size k, called xc for completed. And this is an array of row vectors of size k and the array of size n, one for each of the observations that we have in our data set. We make marker variables for the observed and for the missed. And then we just loop over all the rows, and we loop over all the columns. If R in that cell is 1, then we pluck the value out of the vector of observed ones, the ones that were not missing, and we stick that in the corresponding place of xc, and we bump up our marker for this one was observed. If R is 0, then we pluck a value from xm, where xm was declared in the parameters, stick that in the appropriate place of xc, bump up our missingness marker for the missing values. When we get through from both of those loops, we now have an array of size n row vectors k where all the elements have been filled in. Some from the original observed values, some for the proposals of the missing values that we declared in the parameters block of our stamp program. We have a likelihood statement, basically, that the whole thing, xc, is multivariate normal, conditional on mu and the Cholesky factor L, and we can have priors on mu and L. So, you know, you might think Amelia is doing all this like complicated stuff, but really what it's doing can be boiled down to a stamp program that fits on 2 slides, and you get sort of genuine Bayesian stuff out of it. I put a little bit how to call this some R that you can read through, but we're running out of time. So, okay, if that's sort of our base, how can we, you know, improve our multivariate normal imputation going beyond what Amelia could do? We could, you know, go to a correlation matrix and a standard deviations parameterization, because we know how to put priors on the Cholesky factor of a correlation matrix. We could stratify this by any fully observed grouping variables. So we could have a mu for group J and a L for group J, and we could do hierarchical partial pooling stuff across observed groups, like, you know, what state are you living in, or are you male or female, things like that. We can have prior information about the parameters that go into the multivariate normal distribution in order to have more regularized imputations. We can do transformations. So Amelia will like let you take the logarithm of a variable that's strictly positive or something like that in order to make the assumption that everything's multivariate normal make more sense. What you can do in Stan is have transformations that depend on parameters, like Box-Cox, or, you know, a bunch of other transformations that involve an unknown parameter, and you can update your beliefs about the transformation parameters along with your beliefs about the multivariate normal parameters, along with your beliefs about the missing values or the true values of missing data. And perhaps most importantly, it's easy to relax the assumption made previously that the data generating process is missing at random. That is to say, R contains no information about the missing values once you conditional on the observed values. And you can think of a lot of situations in which missing at random is a ridiculous assumption, and the base case of missing not at random or not missing at random is the more appropriate one for a lot of variables in the social sciences. But if you include or you add on to your Stan model some sort of logit probit thing for is, you know, this or that cell of R 0 or 1 as a function of xc that you already stitched together, now like that part of the model is also providing information about what the missing values are, and you're getting, you know, better imputations under more realistic assumptions. Okay, so out of time, out of weeks for the semester, we still have the final. We'll have a review session next week. It's already been scheduled. I just can't remember what time it is off the top of my head. I'll have office hours Tuesday. I assume the TAs will be having office hours whenever they have office hours. Certainly available to answer more questions that you might have on Piazza. The final is going to be at this time, but not in this room. It's going to be somewhere in IAB. Again, can't remember the exact room, but it's more conducive to taking an exam. I believe it is on May 7th. Is that a Tuesday? Anyway, it's on the registrar's final exam schedule. It will cover the whole semester, but obviously we've covered way more that can be asked about in 3 hours. So we're definitely going to be hitting the highlights. I mean, everything was a highlight, but the highlights. So, you know, there's going to be a question where you have to write a Stan program. There'll probably be some stuff on missing data because we haven't had a homework about that yet. There's going to be, you know, can you do stuff with BRMS? Can you do stuff with RStanR? Can you make diagnostic plots? Can you, talk about the interpretation of, these things in Bayesian context, stuff like that. And that's, really about all you can ask about in that amount of time. So you will be using stand drawing from posterior distributions and whatnot. It won't be any models that take like more than a few seconds. So it's going to be small data sets and stuff like that. So it's not going to be sitting there for like hours or minutes doing computation, but you are going to have to be able to, execute code and stuff. So bring your laptops, bring your chargers. They have plugs in the tables there in IIB. You can use your notes in like the website and the books and all that stuff. Is there anything else you're getting? If so, I'll put it on Piazza. So yes, definitely put the time of the review session, whenever that is. I think it'll be like Wednesday of next week, something like that. Anyway, the semester's over on Monday, so during the study days, sometime, there'll be a review session. Questions? Nope. Okay, well, I'll see you then. If not, in office hours and stuff like that before.